So we define an idea of what we mean by interestingness as the response of the Sobel X and the Sobel Y convolution mask, and then pixels that have a very high response, we consider them to be interesting. Other pixels we consider to be less interesting. So that's the first part of our intelligent zooming algorithm. Now, what can I actually do? Well, now the idea would be, okay, well, we just want to get rid of these pixels, right? The sky pixels. But that's not quite clear how you can do that without significantly changing the geometry of the picture. So instead, what we want to do is we want to remove one column, and later on it works the same for rows, but let's focus on columns for now. In order to reduce the size of the width of the image, I want to remove one column out of this image. Now, in order to not introduce artifacts, I want to make sure that it's kind of connected. So it has to be a connected column. So instead of just want to be able to go up and down here and extract one column, I want to be a little bit more flexible and say that if I have non-interesting pixels here, right, those pixels, and I have some interesting pixels here and here and here, and then I have some interesting pixels here, I want to be able to continue to extract the uninteresting pixels. So then the column that I would actually remove would be this. Right? So I'm allowed to shift one step to the left or one step to the right. And the reason why we want to have this kind of connectivity is otherwise I may have a picture here with a house and another house, and then if I just remove these pixels here as columns and these pixels, then the two houses are going to move too close together. Like the shape is going to be completely distorted. Higher chance that the shape is going to be distorted. So I want the column of pixels that I extract, I want that to be minimized. Connected, I want it to be connected, and I want the to that column to represent the minimum amount of energy in the picture. Okay. So now our problem is like this, and I just draw a small one here. So let's take some random numbers for our gradient. So 10, 5, it's the absolute, so they're all positive, right? 100, 90, 7, 3, Now I can take any path and I can calculate the sum of the gradients, and that will give me a value for the interestingness of that particular pixel. So here, this one would be 140, 143, right? So let's see, let's make that one. That one a little bit. Let's take this one here. 143 is pretty high. If I go like this, 1, 2, 3, then I have, for the blue one, I would have 105, 114, which is much better. So let's make this one here 500. Otherwise, this column would be the least energy one. Then I can do, what else can I do? 7, 3, 50 will be 53, 60. Here we'll get 60, so on and so forth. So every time I move, I can start at the top with some pixel, right? Then I go down. Every time I go down, I have 3 choices. I can go here, I can go there, and I can go there. Now when I'm here, I again have 3 choices. And I want to find the one that minimizes the sum along the path. Right? And now this looks very much like a dynamic programming problem. Because what's the problem then with implementing this? Yeah, and why? How many choices do we have at the top? No. Yes, we would have 4 in this picture, but usually I can start anywhere here, right? So I have width of the original image, choices to start, okay? And then now for each one of those, I have 3 choices, right? But that only gets me from the top to row number 1, right? Then from here to there, I have all of this multiplied by 3 choices. And that's where the exponential explosion comes in. If we just want to estimate this, then I guess that would be width times 3 to the power of rows minus 1. So if you have a 640 by 480 image, this will be gazillions of billions of universes lifetimes before you will get an answer. Right? That you cannot exhaustively search. No way. Even if you update to and you buy your Mac M4 and you buy a bazillion Mac M4s, none of them can do it. All of them combined could not do this. Right? And if everybody on Earth would buy a bazillion of them, it would still not be enough. This is an enormously large number. 2 to the 100 to give you a landmark. 2 to the 100 is the estimated number of electrons, protons, and neutrons, elementary particles in the entire universe, right? And this is 2 to the 100, and you're like 3 to the 480, which is way, way, way beyond that. So, how can we solve that? And now, uh, the answer is dynamic programming. Now, what we need for dynamic programming, actually, if you have a problem like this, and they occur very often, machine learning, reinforcement learning, they occur very often. Any kind of programming puzzle, they like to use them, and many other applications, all kinds of things. If you implement an editor, the minimum editing distance between two words, or if you need to do a spell checker or something, or a fuzzy search engine, then the minimum editing distance is also a dynamic programming problem. We used it in our stereo vision that we used for our urban search and rescue robots. So we had two cameras and trying to match and understand what the world looks like using the two cameras is a tricky part. And most commercial stereo vision algorithms are based on the idea of calculating how much a pixel shifts, right? That's the idea for stereo vision. You want to take picture one, picture two, and then you want to see how much the pixel has shifted in picture two as opposed to picture one. That tells you the depth to that particular pixel. So that's very useful. That's what humans use if we do anything like within arm's reach, any kind of three-dimensional task. Now, professional commercial stereo vision systems are very tightly aligned. Their frames are very sturdy. The cameras are made sure that they match exactly. And the color response of the two cameras is usually finely tuned so that they both return the same brightness for the same pixel. We use two webcams that we bought very cheaply. So, our mounting wasn't exactly right. There was some error in it. The color response was different, so that made it all a bit tricky. So then we came up, our first approach was to say, well, pixels are really difficult, but the fact that you look at picture one and then picture two and you say this pixel matches this pixel, you don't really have much. And I believe that is actually a good approach in lots of computer vision systems. So we've used that in other computer vision problems. But the idea is if you make your decision pixel by pixel, then you really have very little information, very little proof, very little support that this is the actual match. Because it's a single pixel and maybe it's 3x3 environment. So our first approach was to say, well, we cannot really do pixel by pixel given the system that we have. Instead, we were using colored regions. So we would extract uniform or colors regions in the image where that didn't have any strong gradient in them, like that green wall, the door, and the door. And then we would extract the entire region, and then we would look at the top left corner, and then we would match the top left corner of that region to the top left corner in the other image. And that was super robust because you have hundreds of thousands of pixels in a big image that are all part of that region, so they kind of all support that this is the top left corner. Right? So we didn't have, because the problem in stereo vision for us was that if we did a mismatch, if there was only one pixel that it said it matches this pixel, but actually matches this pixel over there, then it would introduce like many ghost obstacles in front of our robot, and the robot would refuse to drive because he thinks that there's something in front of it. Our region-based approach got rid of that problem, but it was quite slow. So then we thought, well, actually, the entire region is like a little bit much. We don't really need that much support. So then we were just doing line extraction. So we extracted lines from the image, line segments, and then we were matching line segments. Like this one there, black, 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 we would match those in the stereo image. And for that, we also used the dynamic programming in order to make that fast enough. Because then you have two line segments, but one is 5 pixels long, the other one is 7 pixels long, and you need to figure out where the start and the end points of those are so that you can match them. Here's the black and white image. So here it's on the order of 3 to the power of h. We give you the first multiplication there for free. And you can see the computational complexity. So for 17 pixels, you're already looking at 1.2 million. And that's a picture with 20 rows, which is a tiny, tiny picture. If you want to zoom that, I don't know what you want to zoom to. But this is the kind of curves that you get every time you're dealing with the exponential growth. It basically is completely flat, and then there's a wall, and you're not going to get over that wall. Now, okay, then you say, well, maybe I don't have to search exhaustively. Another idea would be to say, well, I just take the minimum all the time, right? So here I start here, 10, 5, 50, 50. So then I pick this one, 5, right? Then I look at the 3 possibilities that I have, 5, 7, okay, 9. Then I would get this path. This path is really good, right? It's 12, 21, which is actually the minimum path that we can get out of the minimum seam that we can get for this particular image. However, it's not guaranteed to be the minimum path. Because, let's say, if I change this to if I change the map so that it looks like this, and I make this 51, then the greedy algorithm would go through and pick this one, say, oh, 10, it will pick 10, so make it 100. We'll pick this one with 50, and then, okay, 107. So our greedy algorithm would pick this path, which is 157. Whereas if we had taken 51, 7, and 9, we would have gotten 67. Right? So now our greedy algorithm runs very fast. The expected runtime would be, what would be the complexity of that algorithm? How many pixels do I need to look at for the greedy algorithm?
The first one is the width.
The width, yeah, and then?
First one, then pick one of the two.
Yeah, then I only have 3 possibilities, right? And I pick the minimum one of those. So that's +3, +3, +3, right? Up to rows -1 times. So that would be width plus 3 times the number of rows -1. In the big O notation, we don't care about the -1, right? So that's super fast. Anything linear is a very efficient algorithm. So it runs very fast, but it doesn't give us the correct output in some cases. A lot of times it'll give us a reasonably good scene to extract, but it won't be the optimal scene in that image. So can we sort of combine the idea of the greedy algorithm and the and the exhaustive search without having the penalty of astronomically long run times? Now, dynamic programming is what you want to use for this particular problem. So dynamic programming was invented by Richard Bellman in the 1950s. It's interesting because actually it has nothing to do with programming, and it's also not really dynamic. So the name is actually probably one of the worst names in machine learning programming. And he actually gave an interview once when he said, "Oh, I had to apply for a grant, and I wanted to call it dynamic caching or something like that. But then I didn't think anybody's going to pay for that. But dynamic programming, he thought sounded pretty cool. So that's why we're stuck with this name now." So our picture has 474 columns, right? Now, even if I say, well, they kind of all turn into 3 of those, right? Then we must be, when we look at calculating the minimum pass, we must be redoing a lot of the work, right? We're doing an extremely huge amount of extra work that shouldn't be necessary. That's kind of the first indicator that a dynamic programming approach may work. Okay? If you have a problem where your complexity is 3 to the 8, but each one of those is completely different, then dynamic programming is not going to be able to help you. Right? There has to be some part of the problem, some subpart of the problem that we can reuse, that we can cache the solution and we can reuse it in further computation. Now, the reason why that comes up is because our problem structure, when we look at this, is not really a tree, which is what the 3 to the power h implies. They're not all completely independent counts, because if I'm here and I'm considering this part, this branch here, and then try and find the best path from here to the goal, right? Then that information would also be interesting when I consider this one and when I consider this one, right? Because they all have to look at this particular path from here, the cheapest path from here to the bottom of the image. So a lot of structure in this particular problem. So here's a table. That I create, which just has numbers from 0 to 99, and it's a 5 by 9 table. So now let's say this is our image and the gradient map of the particular image. So that's the absolute of the gradient for that particular pixel. So we can generate different paths at random and calculate what their cost would be. Here 129. If you look at that code, we start at a particular location and start. So here my path is simply -1 from -1 to 1. So -1, 0, 1, which means -1 is go to the left, 0 is go straight down, 1 is go to the right. Number of pictures and then some start pixel, start location. And I can calculate that, and I can calculate the energy along that path, which is simply the gradient response. So then I take 5 of those and I can print them. So here's an implementation of the greedy algorithm to get the height and the width of the image. And then we first iterate through the first row and look for the minimum. Then we remember where that is and what that value is. And then we start at that minimum index. Our path now is that at the 0th row we're at location X. And then we go through for each row. We look at the neighbors. If it's in the image, so it's not out of bounds, then I check if it's the minimum one, then I remember what it is. Then that would be my next X2, and I can append it to the path. So this would be the 3D path 0, 1, 1, 2, 1, 3, 0, 4, 0. So that would be 0. Oh yeah, I made another one. This is just the first part of the image. So this is just the first 10 rows. So that I can print them out. So dynamic programming is an optimization technique developed by Bellman. Consists of 4 parts. 1, break the problem down into subproblems. Solve each one of the subproblems. Remember, cache the solution to the subproblems, and then reuse those solutions to the subproblems to create the solution for a larger part of the problem. All dynamic programming works that way. And I guess initially it's a little bit intimidating, because one way where you can easily see the recursive structure of a problem is if you implement a recursive algorithm. If your algorithm is a recursive algorithm, then it's very easy to extract the structure for it from for your dynamic program. The simplest one would be the one that you're all familiar with, would be the Fibonacci numbers. Right? Because one implementation of Fibonacci numbers, so the Fibonacci numbers are, what are they? 1, 2, 3, 5, 8, 13, 21, so on and so forth, where every entry is the sum of the previous 2 entries. And Fibonacci of 0 is 1 and Fibonacci of 1 is 1 as your base case, right? So of course it's very easy to implement. In Python, we could implement a routine to calculate the Fibonacci numbers, which says if n is less than or equal to 0. So this will be the first Fibonacci number, but we'll give it an index. Yeah, if n 1 to, if it's less than or equal to 2, then we return 1. And here we assume that n is larger than 0. Else, what would we put in the else part? Yeah. Fibonacci of n minus 2 plus Fibonacci of n minus 1, right? And that implements this part here. And this implements those two ones, right? So for any first year programming course, you probably have seen this. It's a very popular recursive algorithm. It is a recursive algorithm because I define Fibonacci here and I call it inside of my definition. Right? That's what makes it recursive. Now, this is a terribly inefficient implementation for the Fibonacci numbers. You would never do this in practice. It's simply only useful for example, introduction to recursive programming. And the reason for it is in order to calculate Fibonacci of 1, 2, 3, 4, 5. Right? In order to calculate that, I need to call, if I just look at the calls for Fibonacci, for this Fibonacci subroutine, then I will execute here Fibonacci 5. 5 less than 2? No. Less than or equal to 2? No. So we call this. So here I call Fibonacci of 4 and Fibonacci of 3. Right? In order to calculate Fibonacci of 4, I call 3 and 2. Right? In order to calculate Fibonacci of 3, I calculate Fibonacci of 2, Fibonacci of 1. Here, in order to calculate this, I have to calculate Fibonacci of 2, Fibonacci of 1. Here, I calculate Fibonacci of 1. No, Fibonacci of 2 is base case. And Fibonacci of 1 is a base case, base case, base case, base case. And then all of that gets passed back up the stack, and I can finally return my answer. By looking at this recursive algorithm, however, it's easy to see the structure of the problem and the amount of extra work that we're doing. Because which parts are repeated? Well, here I calculate Fibonacci of 3. Here I calculate it again, right? Fibonacci of 2, I calculate 3 times. 1, 2, 3. And Fibonacci of 1, I calculate 1, 2 times. So you can see that actually a lot of the work that I'm doing, I'm repeating, right? So this is where the structure comes out of. That's where the why looking at it, developing a recursive algorithm to solve your problem allows you to easily recognize the parts of the subproblems that you can catch. Because it now makes sense. You can easily say, well, it's done to calculate Fibonacci of 3 twice or Fibonacci of 2 3 times. So that's the first step in your dynamic programming, and in order to be able to figure out a way to apply dynamic programming. What would be the subproblems for our seam carving? Huh? The minimum pass downwards, right? The question that I always ask is, that we need to answer is, in order to figure out what the cost of this path, of any path would be whatever I do at the top, right, to some pixel, so it'll be this part plus the value of that pixel plus the minimum path going downward. Let's say here going to the right. Right? Now, this part I calculate. This part here, that one I can reuse 3 times at least. Right? Because there's 3 pixels that all want to know what's the minimum pass from here to the bottom of the image. So this is our recursive solution for the seam carving problem, extracting the minimum column. Other algorithms, by the way, that are based on dynamic programming are Dijkstra's search algorithm for finding a path through an environment, and Floyd-Warshall, which I like quite a bit. It gives you Dijkstra gives you from a single source to a goal, to any goal, but Dijkstra gives you any point to any other point. So once you calculate it for an environment, you can know the cheapest path from one point to any other point. So from any initial point to any goal location. And Levenshtein, which is the minimum editing distance if you implement spell checkers. Or any other kind of fuzzy searching. So here, this is what it does. So DOS, is that misspelled? Should that be house or cat? DOS and dogs would be much more common. So then you need to, your auto-suggest is basically what is doing that. So when we apply it to dynamic programming, what are the subproblems? The subproblems are from a particular node, pixel, what's the minimum energy path to the edge of the image, which could be either up or down. And as you'll see, we'll switch directions in the seam carving program. So here we have a couple of random domain here. So our dynamic programming table, we create a table with the minimum energy for that pixel to anywhere on the top row of the table. And the reason for that, why we can do that, is because as I fill in, that's the really clever part, as I fill in this particular table, I want to know from this pixel, what's the minimum cost to go to the top? Well, we fill that in one row at a time. So we start at the top, then we can use the information that we just filled in row 0 when we enter row number 1. Because, let's look at our sample table here. So now I maintain two parts of two pieces of information. One is the actual table here, but I also need to remember what the current best path is to this particular pixel. So this is like one strip of the image, and there's more pixels on the top, more pixels on the bottom. So to get to this pixel from the top, it'll cost me 124 when I sum up all the gradients, and then I have 19 there. Right? So then I can add up a Okay, then we start out with our table here with the random numbers. And this is our first row, right? So far, there's nothing above. So the cheapest way to get from the top to here would be 16, right? 11, 15, 12, 14, 10, because there's nothing above. So that's how we can initialize it. So now, what do we do for the next row? Well, here, to figure out what the optimal path is for this pixel, I know that it has to be one of these two, right? Because those are the only two neighbors that I have that are above me. So my cost is going to be 16 plus what the minimum cost is here, which is 16, or 11. So in this case, 11 is better, right? So our cost would be 16 plus 11 should be 27 there. For this pixel here, I looked what the minimum cost is. I have 16, 11, 15. It would be this 11 here. So my cost here would also be 27. For this pixel, I have these three possibilities, 11, 15, and 12. Then I would take the 11. So here I have 26. From here, 15, 12, 14, 12. So 27, I can update my sum here, 27. Then we have 11, 12, 14, 10. That will be the 10, so 21. And here I would have 26. Right? So as I go through, I only need to look back one row in order to fill in what the cost of the optimal path is from myself towards the top. And the only information that I need in order to be able to make that decision is the optimal cost so far to the row above me. So I can fill this out for the entire table. So the minimum energy seam will go through the top neighbor with the minimum energy, with the sum of the minimum energy so far. So the minimum energy pass through that pixel will be the gradient magnitude of that pixel plus the minimum path of the top neighbor, which is left, right, or bottom. So I can update now the information as we go through. And it is kind of cool that you can do all these animations with Matplotlib. I like that a lot, but on Google Colaboratory, if you use too much memory, it requires quite a bit of memory, so then Colaboratory slows down. So this is how we kind of fill in the table. Here, the first row, just take the gradient we set up. So remember the sum. So next row, we'll take 43 or 86 plus the 62, which gives us 105. From here, we look 86, 43, 59. So that'd be 43, so 27 plus 43 is 70. So then we fill in the second row. You can see how the number changes as it considers the alternatives here, the 3. So 15 plus 66, 81. And it just goes through like that until we fill in the entire array. Oh, yeah. And now I actually have all the information to extract the minimum energy seam, because how do I find it? Like, how is this information useful now? Now we start at the bottom of the image, right? And we check. And here I just need to find the one with the minimum sum, which is 102 here, right? So that means the minimum seam is going to go through this pixel. So now I know where it ends. How do I know where it comes from? Yeah, now it must be one of these 3, so I just need to look at the sum, and then that would be 89, so we would go here. And then from here, it will be 50, so we go up 1, then 35, and then 15. So this will be the minimum seam that I can carve out of this particular image. Initialize with color. weird. How come it's not? Ah. I ran the wrong cell. I mean, it's not, it's right, it just takes a minute.
Oh, it's funny, you actually shows Smart Zoom. I don't know what Smart Zoom is.
The Smart Zoom,
Or sorry, that's the Zoom.
the Photoshop
Yeah.
is, they call it Smart Zoom here. And this is the video. So carve now is a color for some reason. So you can also see how the algorithm is very cheap as far as memory is concerned. We basically just need one extra two-dimensional array the size of the image. So basically we need a copy of the image. Or just as much memory as. And anyway, here then that's the code for finding this minimum energy scene. We start at the end of the image and then look for the look for the pixels that have the minimum energy, one of the neighbors above that has the minimum energy. So here we calculate the array that I called carve, which includes the sum of the minimum path to the top. And then to find the path, we take the minimum from the bottom row and then look at the top. So we go upwards. First we go down in the image, then we go up. So the complexity of the algorithm would be the width multiplied by 2 times the height multiplied by 3, because we need to check for 3. So that's very cheap. And we can compare it to the greedy path. So this would be our minimum energy path. So now I have that path, right, that we found. Now I can remove 1 pixel in every row. And that pixel is going to be connected. Like all of these blue pixels, all of these that are labeled in blue, I'm going to delete them. So things are going to shift a little bit, but they're not going to shift so much usually that the structure is going to be completely changed. So here we remove the path, we have an image, we have a path, and then the new image is the old image height, and the width is reduced by 1, because we remove 1 pixel for every row. And so then from the new one is for row Y, it's going to be from 0 to X, will be the image, and from X to the end, it will be from X plus 1. So YX is going to be removed. So then we have our new pixel here. The image started with 475 pixel width, and now it's 474. Now we can put this into a routine like that carves the seam. And now instead of just removing 1, I can say do this n times in a row. Now, unfortunately, if I want to reduce the width of the picture by 10 pixels, then you may think that one way to do that would be to look at the bottom of the picture, find the minimum seam, start, then say, okay, remove this one, the first one, the second one, the third one, right? If I want to remove 3 pixels. However, that doesn't work. Why? Pardon? You have to recalculate for the entire image after you remove 1 column. And the reason why you need to do that is because the minimum path may be shared. Let's say here's my picture, and here I have 50, and here I have 51, and those are the 2 minimum ones, right? And if it goes like this, right, then no problem. I could cut these 2. But if it goes like this, and they share the path, then from here on upwards, I would try and remove the same pixel twice, which I can. Because I'll remove this one, so that pixel and this whole part here is going to be removed. So it's gone, so when I want to remove this one, those pixels don't exist anymore. So that's why the simple approach is to simply recalculate that remove one pixel, then do the whole process again. That's guaranteed to be correct. You could also check if you want to remove n pixels. You start with the minimum one, remember the pixels that you remove, then you check the next one and see if they share any of the pixels. If they do, then you have to rewrite, otherwise you can but then the logic becomes a lot more complicated. And it's usually not worthwhile the extra speed. Like, this is more like a slow operation for the user anyway. So here, that's basically the loop, right? The number of iterations, we calculate the gradient, we find the minimum energy seen, and then we get our path, convert it into an array, and then remove that path. And then we do that again and again. So here I removed how many? Half. So half of the pixels here I removed. And then also we can take the picture, and I've done it for column. Usually what you do is you first remove a column, then you remove a row, then you remove a column. If you want to reduce both parts of the image. If then you need to worry a little bit about the aspect ratio of the image. So here then this would be the result. This is our original image. This is zoomed by a factor of 2. And that would be if I crop the image, right? If I want the most interesting part, I lose the tower of the pagoda. The pagoda now is, the top is gone, right? Like if that's just cropped, that's just this part shifted over. And this is our intelligent zoom here by a factor of 2. And you can see that it maintained a lot more of the detail. Right? The pagoda, the temple, all of this stuff is still there. Clouds and sky and these parts here in the background, those are all much further removed. I mean, most pixels are removed in this area here. You can see it looks a little bit fattened now, right? Because the pagoda stays in, whereas the other parts are shrunk together. So I think here we just so here we do it with a picture of Taipei 101, and there this would be smart zoomed part with different resolutions. So here 80 by 60 out of 120 by 120 picture. Now that's one application of it, right? To remove, to zoom or make a more interesting thumb scale, which includes more interesting parts of the image. But another interesting thing that we can do is we can use the same algorithm in order to remove unwanted artifacts. So if you have a person in the picture, but you don't really want them there, right? Like your ex-girlfriend or your ex-boyfriend, and you want to eradicate them, then you can also do that using scene carving. And how would we do that? If I have a picture, and this is my former boss, so I want this part to be gone, right? Then what I can do is I can calculate the minimum energy, right? But then I have a user interface where I can set the minimum energy here to 0, right? If I set the minimum energy in this area, so I have like a brush, I can paint over it, and wherever I paint the brush, it sets the minimum energy to 0, then that's where the algorithm is going to cut. And that's how you get rid of unwanted artifacts in your picture. So this is also also implemented in GIMP and Photoshop, I think, but it's called something like Smart Remove. And there you have it. That's the lecture on scene carving. Now and you can run the notebooks. They should all work now once the carved image should have been a it'll just take a while to run them. So here it shows you when it changes the numbers, the new numbers that it has in for the dynamic programming cache and how it extracts the dynamic path. So that's it as far as the scene carving is concerned. It's a pretty neat algorithm. More importantly, it's also a really nice example of dynamic programming. It shows all components that you need in order to convert a problem into one that may be solved much significantly faster using a small amount of memory. Like this is phenomenal, right? We're going from a bazillion years to less than 100 milliseconds or something. So well worth the effort to think about the recursive solution and the caching of the subprompt. Now, the other thing I wanted to discuss today is to give you an idea. I will post the project with the German students for you guys, since you are in the computer vision course later today or tomorrow. But here, this is the idea. We want to be able to extract the climbing walls from both synthetic images of the climbing wall and real images of the climbing wall, so that with our larger humanoid, hopefully we'll be able to climb the wall. So for this particular path, given a so as a human, if you want to climb that, then basically what they tell you is the color that you need to climb. Here, those tapes, they tell you the difficulty. White is very easy, yellow is a little bit harder, green is a little bit harder than yellow, pink, and then that's as far as I can climb. Everything else is too difficult for me. So I don't know what the other colors mean. But basically, we will give your algorithm a part of the wall and tell you which colored markers, orange or yellow or whatever, you need to extract. And then you want to extract the position of the holes as well as the orientation and the sort of type. Some of them are like this. If they have a top hole, then we want to extract that because that's, we know that the robot can grip there. And so then at the beginning you may get a picture like that. Selection? No. Oh, you can do this now. This is new. Usually you can only do like rectangular. Okay, let me try that again. How come I don't have this? Here, this one. No. Maybe like this. So we'll give you this as the start image, except it'll be rectangular because I don't know how to, I don't want to implement having to select using the lasso thing. But then that allows you to get an idea of what the colors are, and then you need to find the rest of the handholds. And after you have the handholds, then you want to be able to calculate their position. Say like this. The outline as well as the gripping part. Like here, this guy would be like that, this guy like this. Now OpenCV can do that actually quite easily. You can calculate the approximate polyline fit to a shape. So after you extracted the shape of the hole, you can apply the contour algorithm in order to get the contour. Once you have the contour, you can convert it into line segments. Once you have the line segments, you want to figure out which one the top is, because that's where you usually can roll. And we don't, I mean, obviously, you could make this arbitrarily difficult. Actually, that heuristic works pretty well. But this one here, for example, this hold here, there's nothing you can hold at the top. You have to hold it from the bottom. So sometimes you have a hold that you need to They have a name for it. What's the name for it? Not an undertow, but anyway. So my robot doesn't do that. We will do that next year. First year we start a little bit simpler. Also, we will modify the pictures so that these two here, the two orange that are completely overlapping, we will make sure that there's a little bit of a gap between them. I think this one, you may still have enough of a gradient here to be able to distinguish those two, but otherwise that will be quite difficult. So we ignore those. And also, this hole here, our algorithm would put the hold at the top there, the grip, but of course this is actually like a tube coming out, so you can use right and left hand. So we ignore this type of hold as well. So they'll be removed before we send you the picture. So your pictures will have holes like this, the standard ones. The ones that are too difficult we'll remove from the picture first. And so I've posted some of the sample pictures. This one here is actually okay. I don't think there's anything that's problematic there. This one is actually a hole that has both sides. So if you draw the green line left and right, then that would actually be okay. This one here, the white ones. So there will be, we'll give you these sample images from the real climbing gym, as well as I'll generate some more synthetic ones from the simulator. And then you will implement your algorithm. We'll call that the training set, and then we also take some other pictures that we don't show you until the demonstration of your assignment, and then we'll see how versatile and robust your algorithm is. Because if I ask you to print out the location of these holes, then of course that would be quite easy. You can just calibrate it for blue, and or just by hand click on where the holes are. But the idea is that it should work for maybe not all paths, but quite a few of them in a standard climbing gym. This one here, we would remove this one and that one simply because they're actually three-dimensional. They're not on the wall. So then being able to determine the distance of these two would be not possible without some additional piece of information, like the width of the thing, or the this hole's geometry, or this hole's geometry. So any questions about what you are supposed to do here? So my approach would be, I think it's certainly doable. The approach would be to try and figure out what the background color of the wall is. That seems to be quite important and interesting. And then to extract contours that are not that background color. And from those contours, pick the ones that could be orange or are orange, and then find the contour do the polyline approximation and take the top one in order to identify it as the hold location. And for the, so you map a line here. Once you map the line, we need to know the position of the line and also the angle of the line. So the orientation. Because, for example, here you can grab it like this, but you wouldn't be able to grab it like that.
So you're using half line to get the line angle.
No, I don't think you want to use half line, because half lines will give you line segments. You can try it, but I don't think you will get very good line response. Here you may get some.
Because it's vertical.
No, here this I would probably recognize as a line. Here those lines are pretty small. There's other lines. All of these may come out as lines. The tape will come out as a strong line. So either you start with the color, so you get part of the picture, right? So you get like this part, and then you calibrate what the orange pixels look like and what the background pixels look like. And then you find globs of those. Once you have globs of those, then you can calculate the contour of that, which means the outline. Once you have the outline, then you can calculate the polyline approximation. Then you map lines to it. So you only map lines to the part of the one hole, not globally over the image. I don't think that would give you a good response, but you can try it. But first find the blocks. Once you have the blocks, then the lines you get quite easily from the shape. Once you have the shape, you can also register it as a standard hole if it's something like this, like the hand kind of thing, you could match it.
So in the Python code, we have a bunch of NumPy array to correlate to masking the color, like yellow NumPy array, and then red NumPy array, then green.
I would not do that. Your color predicate usually is either the minimum and maximum red, green, and blue channel, right? So you just set threshold. Or what I usually do is minimum and maximum red, green, blue, as well as the color difference channels, red minus green, red minus blue, green minus blue. Because otherwise you get some fake, and then you need to find enough, enough pixels has to be large enough to be a hole. If it's only 3 pixels in that image, it's not a hole, right? So must be the connected component. So then you find the connected components of all the orange pixels. You break it down, and then it'll find 1, 2, 3, 4, 5, 6, 7, 8 here. I'm not sure if it'll take this one as 1 or 2. Then you have the components, then you calculate the contour of the component, and then you calculate the polyline approximation. And that should give you a nice result. And then be independent of the background color. Robust to changes into light. Okay, good. Then if you haven't demoed your assignment 1, then we can do that now for the next 30 minutes. And that'll be the end of the class. Or the end of the lecture material.
What table will you use?
Yesterday we used just the cardboard there.